It's my great pleasure to introduce our colloquium speaker today, who is my great friend, Hiroshi Ooguri from Caltech, and also my collaborator, one of my very frequent collaborators, who's given me double pleasure to introduce him. Actually, he has been here for a number of times, in addition to regular visits to Harvard over the past, I don't want to mention the number of years, but let's say about 30 years or so. He has also spent a sabbatical in 1992 here for 1 year, and also a sabbatical 2 years ago for half a year. So we are very pleased to have him here again. He really needs no introduction, but nevertheless I will do this for the people here who may not be, who will be very young and maybe not in our field. But anyhow, I will mention he finished his graduate study in 2 years and became a tenured faculty member at the University of Tokyo in 1986. He was a member of the Institute for Advanced Study in Princeton and was appointed an assistant professor at the University of Chicago before he received his PhD from Tokyo in 1989. There's no contradiction here. You should ask him what that story is. He was an associate professor at Kyoto University in 1990 to 94 and returned to the United States as a professor of physics at UC Berkeley in 1994. In 2000, he moved to Caltech, where he is the inaugural holder of the Fred Kavli Chair. So at Caltech, Hiroshi served as the deputy chair of the Division of Physics, Mathematics, and Astronomy, which is equivalent of Vice Dean of Physical Sciences from 2010 to 2015. He led the establishment of the Walter Burke Institute for Theoretical Physics and was appointed as founding director in 2014. In 2007, Hiroshi helped establish the Kavli Institute for the Physics and Mathematics of the Universe in Japan, where he is a founding principal investigator. He has been a member of the Aspen Center for Physics since 2003 and was elected its president in 2016. Ooguri is a fellow of the American Academy of Arts and Sciences and an investigator of the Simons Foundation. He has received the Eisenbach Prize for the American Mathematical Society, the Humboldt Research Award in Germany, and the Nishina Memorial Prize in Japan. His popular science books have sold over 250,000 copies in Japan. And his science movie received the Best Educational Production Award from the International Planetarium Society. So without taking more time, I'd like to introduce Hiroshi Ooguri for our talk.
Oh, thank you. Well, Cameron, thank you for your overly generous introduction. So I have had many wonderful time at Harvard, and some of my important, most enjoyable work have been done here. So it's a pleasure to come back and an honor to give a colloquium today. Somebody asked said that I'm over the list, and I want to explain. I'm married to a woman whose parents run company that produce and sell men's tie. So if I get filmed without wearing this, then I get into trouble. So, and moreover, I get infinite supply of men's tie, so why not use it? So I'd like to talk about constraint of quantum theory of gravity. And so what I would like to tell you about is that why the unification of general relativity and quantum mechanics, which has been the homework from the last century, has been so difficult, and why superstring theory is important in this context. And so holographic principle is something we hear a lot these days, and I would like to tell you about it. And then also what's known and not known about quantum gravity. So let me first tell you why it has been so difficult. So the typical answer, if you ask people, typical answer you get is because Einstein's gravity coupled to finite number of matter is not renormalizable, and you can't use it to do quantum gravity calculation. Well, that's partly true, but no, it's not an entire story, so let me begin with that. So for example, here is an analogy. So in nuclear physics, we have mesons, and pion is an example of that. So here is an effective Lagrangian of pion, and if you look at it and do naive power counting, you see it is not renormalizable because F here is a dimension full parameter. So that means that well, F actually is about 184 MeV, and but however, we can still use this Lagrangian usefully. You can even do some quantum mechanical calculation using this one. As far as we are looking at physical phenomena whose energy scale is less than F. So what we do is that we expand observable quantities like scattering amplitude in power of energy divided by F or momentum divided by F. And then each term in this perturbative expansion can be calculated systematically. And at each term in this expansion, you only have to renormalize finite number of them. So this theory is not renormalizable. You need infinitely many counter terms. However, to each order in the momentum and the energy expansion, you only need to do finite number of renormalization. So that means that you can actually make predictable, you can make prediction that can be tested experimentally. So this actually can be nicely understood in the Wilsonian point of view of renormalization group. So pion theory is actually not a complete theory, but it's a low energy approximate description of quantum chromodynamics, which is more complete theory of strong interaction. And QCD is actually a complete theory. That we believe that it's well-defined theory because of asymptotic freedom. And we expect that it can be derived by performing the functional integral of QCD while freezing the low energy degrees of freedom, such as pion. So it is, in this sense, it's an effective theory. And the theory itself, this theory is not renormalizable, but you can make low energy prediction, including quantum mechanical effect, and they have been verified experimentally. So in this sense, actually, the situation of Einstein gravity, you can say, is very similar. If you look at this Lagrangian, again, you have a dimension-full parameter here. So this theory is not renormalizable by naive power counting, but it can be used to make reliable prediction, including quantum effect, provided that energy and momentum are less than its cutoff scale, in this case, a Planck scale. And so what cutoff scale means that if you are trying to, if you want to understand physical phenomena whose energy scale is above this scale, then you need more fundamental theory, more theory that is more fundamental than Einstein's gravity. So there are many interesting gravitational effects which contains quantum mechanical effect, which you can calculate by using this theory and make reliable prediction, and you can possibly test it experimentally. So for example, Hawking radiation from black hole, which I will mention more later, is an example of this type of effect, which you can actually calculate reliably. We believe that Hawking's calculation is correct because it is in this context. If you assume that there was an inflationary period in early universe, you can again use quantum mechanical calculation using Einstein gravity coupled to scalar field, and you can derive the density fluctuation, the fluctuation of cosmic microwave background radiation, and I guess I have a typo here, excuse me. And then you can test it against the experiment. You can even compute correction to Newtonian potential. So this is what we learn in undergrad. There is a relativity correction to it, and then there is a one-loop correction. So I'm using the unit when C equals 1. There is 1 over C here, I presume. And then this is the one-loop correction, which actually you can calculate 135 reliably using this Lagrangian. Actually, this number is for pure Einstein gravity. If you have other matter field, this number is changed, but changed in a way that is quantitative. So therefore, the claim that the quantization of Einstein gravity is difficult because it's not renormalizable is true, but it's not the whole story. So what are the issues? So here I would like to list like 3 issues which are interrelated. The first issue is that here I took this Wilsonian point of view that pion theory is a low energy approximation to QCD, and perhaps Einstein gravity is also low energy approximation to some consistent theory of quantum gravity that we do not know. However, within physical phenomena whose energy scale is less than cutoff scale, we can make reliable prediction. Now, is this really true? Does this Wilsonian approach really work in in the case of gravity. So there is actually a subtlety to it, because in the case of gravity, the metric which measures the length between 2 points is actually dynamical variable. So in Wilsonian point of view, it's important that you define the cutoff scale, and you say that you integrate over degrees of freedom only above the cutoff. But if your metric is a dynamical degrees of freedom, can you really do that without violating some of the principle of gravitation? And in fact, there are indications that this kind of separation of ultraviolet degrees of freedom and infrared degree of freedom is not as simple as you might think from Wilsonian point of view. Black hole firewall paradox, which I do not have time to talk about today, is an example of that. The swampland issue that I will talk about today is another issue that indicates that the naive Wilsonian point of view may not work in certain situations in gravity. There is another important and related issue, which is that in the case of pion, we know that it is a low energy approximation to QCD, which actually is a consistent quantum theory. Well, we believe that it is consistent. There is $1 million prize for anybody who proves that it's consistent theory. But the very fact that mathematicians take it so seriously to give $1 million prize indicates that we really believe that this is likely to be UV complete. So we know this as a fact, but is Einstein gravity guaranteed to have UV completion? Unless you construct it, we don't know. And also, there are many interesting questions that we would like to ask that cannot be addressed in this kind of approach, such as what happened at the very end of black hole evaporation by Hawking radiation. So we believe that, many people believe that there was an inflationary period in early universe, but is this really true? Can you derive it from some complete theory of quantum gravity? And what about the initial singularity of universe? So there are some of the fundamental questions that we cannot address without having more sort of UV complete quantum theory of gravity. So let me expand on this second point, because this is related to what I would like to talk about today. So is Einstein gravity guaranteed to have a UV completion? Okay, so in fact, I don't know about Einstein gravity, but we do have some example, I may say existence theorem, that there is a consistent quantum theory of gravity, and that is string theory. In superstring theory, we can compute quantum effect not only to each order in momentum expansion, but to all order in perturbative expansion. And ADS-CFT correspondence, which I will mention later, give you non-perturbative completion of this type of series in certain situations. And its low energy effective theory contains Einstein gravity. And moreover, if you compactify this theory to 4 dimensions, then we find that, in fact, you can have low energy theory which contains several generations of quarks and leptons, and number of generations depend on the topology of the compactification. And you have gauge interaction, which can include standard model gauge interactions. And you have Higgs mechanism. So these are all the ingredients that you need to construct standard model particle physics. So this indicates that, yes, there are possibly consistent construction or ultraviolet completion of quantum theory of gravity, including our own standard model of particle physics. However, as I will try to talk later in this colloquium, that not all low energy theory of gravity have UV completion. So I will give actually counter example to expectation that to this one. So this is actually contrary to what we know about ordinary quantum field theory, for which Wilsonian point of view works. In the case of ordinary quantum field theory, what we believe to be true is that you can write down any low energy effective action, Lagrangian, with given number of derivative, and assuming certain symmetry and existence of number of degrees of freedom, provided that this theory is consistent within the framework of low energy effective theory. So for example, if the theory has gauge anomaly, then you can detect that it's not consistent within low energy effective theory, so you don't expect to have complete ultraviolet completion. But if it is consistent within low energy effective theory description, then you expect that any such low energy description have UV completion. There are indications, and in fact, I will give you an example, that this expectation is not quite true in the theory with gravity. So this is actually the idea of swampland that was first advocated by Cameron, which I will talk about later today. So this is actually, so the contrary, so this is a situation where we may not have a, given effective theory of gravity may not have a UV compression. So this is related to the first point that the naive application of Wilsonian philosophy may not work here. Okay, so there is actually another special feature of quantum theory of gravity. So we know that the physical world has a hierarchical structure. This has been a blessing for us because it is because of that that we have been able to understand physical world so well. So we have atomic system, which was uncovered in 19th century. And if you look at the structure inside of it, you have electron going around the nucleus. And then inside of it, you have protons and neutrons bind together by pions. And then there are quarks in it. So you have this kind of hierarchical structure. And then by probing shorter and shorter distance scale, we uncovered more and more fundamental laws of nature. But this type of hierarchical scale may terminate once we complete quantum theory of gravity. So there are various arguments for that. So for example, you can try to probe shorter and shorter distance by building more and more powerful accelerator. And then because of the Heisenberg uncertainty principle, the higher the energy, the shorter distance you can probe. So that was what high energy physicists have been doing that. But by the time you reach the Planck scale, what happened is that the energy, if the energy at the center of a collision becomes greater than Planck scale, there will be a black hole over there. And then more energy put in, the event horizon of the black hole grows. So you cannot probe shorter distance beyond the Planck scale. So we expect that this kind of hierarchy of scale will terminate at the quantum theory of gravity. So in the sense of exploring shorter distance, we have actually ultimate unification of elementary particles and forces. So constructing quantum theory of gravity is not only just one more step in unifying force, gravitational force with other forces, but it's actually a grander sort of goal of trying to understand what happens at the very end of a hierarchy of scales. So it's kind of fun question. So it's actually fun to think about these fundamental questions. And moreover, we have been making lots of progress in addressing them by requiring logical consistency with known physics. So this is actually a fun thing, and it's highly non-trivial that we can make progress in this type of direction. So let me discuss some of the progress that we have made. And one of the important playing ground for our progress have been the black hole. So I would like to mention first that Stephen Hawking recently passed away, sadly. And one of his important contributions to physics was discovery of black hole evaporation. So the idea is that so in the vacuum of quantum field theory, that you have creation and annihilation of a pair of a particle and antiparticle happening all the time. But if you are near the event horizon, either particle or antiparticle can go inside of the black hole, and the other one can escape without having to pair annihilate. So this is an idea. And then using that, Hawking calculated the temperature of the black hole, and using this standard thermodynamic equality, he predicted that black hole should have this much entropy. It's a pretty large amount of entropy. I guess 1 terabyte is like 10 grams or something like that, if I understand it correctly. So you have a Newton constant over here, and entropy is supposed to be proportional to area of event horizon. So this was a surprise, because how come that entropy can be proportional to area? So we learned in undergraduate that entropy is an extensive quantity, so it should be proportional to the volume of the object we are looking at. So if you have a black hole, it should be proportional to the volume of the black hole. So why is it proportional to the area of the horizon? So this led to the idea of holographic principle, that if you have quantum gravitational system, then the fundamental degrees of freedom for the region of space-time for which gravity is defined is actually on the surface surrounding it. And very interestingly, string theory, which we believe is a complete quantum theory of gravity, does have this feature that was expected. So but to explain this holographic principle and how it is realized in string theory, I need to do a little bit of preparation. And this preparation has to do with D-brane, which was whose importance in string theory was discovered by Joe Polchinski, who sadly also passed away recently. And so the idea is the following. So in string theory, you can have closed string, which is like this, which has no end. and then open string, which has 2 ends. And then if you have end to the string, then I need to tell you where that end. So so namely, if you have open thing, then you need to impose boundary condition on the end. So the end point of open string can be either a point, or curve, or surfaces. So you can have many possibilities. So now suppose that this open string end on some subspace like that, and suppose you consider the process of closed string coming in and open up and end on this subspace and close up over here. You can view this process in a slightly different way. You can slice this two-dimensional sheet swept out by this string in this way. So if you view it this way, then it looks as though you have closed string coming in, and you have another closed string coming out from the surface, and meet and join and going together. This is just as if this subspace is not like a static object, but it is an object that can emit and absorb closed string. This fact follows just from the fact that open string can end on this surface. Now, in string theory, a graviton, which communicates a gravitational force, is coming, the quanta of the gravitation, is actually a closed string. So that means that, in particular, this space, this subspace where open string can end, can emit or absorb closed string, including graviton. So that means that this surface, the subspace, must have energy and masses. It's gravitate. So these objects are called D0 brane, D1 brane, D2 brane, depends on the number of dimensions, and these all have masses, namely energy. So that means that if there are a large number of them, the mass become large, and eventually it can start gravitating strongly and can become black hole. So but this black hole is described by open string. So in certain situations where you can quantize this open string and do calculation precisely, and understand what the Hilbert space of this theory is, you can count a black hole microstate. And amazingly, these two gentlemen who are actually in the audience, Kurman Buffer and Andy Strominger, using this idea of Joe Poltinsky, actually derived in the case when this calculation can be done exactly, that entropy is actually equal to the area of horizon, including this precise numerical quotient, which is amazing. So this shows that indeed string theory is quantizing quantum theory of gravity correctly and is reproducing this important formula. Now, but this is saying something very interesting, because this is supposed to be describing black hole, but on the other hand, this degrees of freedom is described in terms of open string on D brane. So, but this theory of open string does not contain gravity. Gravity is described in terms of closed string. So that means that the gravitational phenomena, most importantly, the fact that the black hole has entropy, is described not in terms of gravitational degrees of freedom, but in terms of degrees of freedom that is not gravitational, the theory of open string. So this led to the idea by from Alzheimer that the ADS-CFT correspondence, he managed to extract some very essential feature of this correspondence and show that the gravitational theory in anti-eta space, which is Lorentzian signature space with negative curvature and maximally symmetric, is equivalent to conformal field theory, which is residing on the boundary. And so this in principle gives you a complete description of quantum gravitational phenomena in anti-eta space, and in particular, the evaporation of black hole by Hawking radiation can be described by unitary time evolution in the boundary CFT. So in principle, this provides solution to the information paradox. Although precisely how the information is preserved still need to be understood, and there are active research going on in that area. But in principle, this shows that there should not be paradox. One of the important things is that this defines consistent quantum theory of gravity, including non-perturbative effect. For me personally, this was a quite big relief, because so actually I became the first year graduate student in 1984 when the first superstring revolution started. And I was studying string theory for many years. never knowing whether it actually exists because it was defined only perturbatively. And it was only 11 years afterwards that there are actually, it was, no, even after that, maybe 13 years after that, that I was told that, in fact, there are situations where you can actually non-perturbatively complete it. So it was a quite a relief that I was working on things, to know that I was working on things that actually exist. And but now it exists, so it's great. And in fact, there are also many important applications of this ADS-CFT correspondence to other interesting programs in theoretical physics, such as condensed matter physics and hadron physics. But I do not have time to discuss them today. Fortunately, one of your colleagues have written a beautiful textbook on that subject, so you can ask him. And instead, today, let me discuss some of the new insights that the quantum gravity provided by using this holographic principle. So before I get into what I want to really talk about today, I still need some preparation. So let me talk about some recent insight into the relation between the geometry of space-time and the quantum mechanical entanglement of a system. So let me use a couple of pages of this, my transparency, to explain a notion of quantum entanglement, which actually first show up in the paper by Einstein, Podolsky, and Rosen. I think term entanglement itself was coined by Schrödinger, I suppose, after this paper appeared. So here's an example. So suppose you have a Hilbert space HA and HB, both of which are two-dimensional. And if you have just tensor product of one of the state here and one of the state here, there are no entanglement between them. But if you consider, for example, what is called Einstein-Podolsky-Rosen pair, like this, then this is maximally entangled. There is actually a way to quantify the amount of entanglement. So suppose you consider any state in this tensor product Hilbert space, then what you do is that first you take partial trace over the second Hilbert space. This makes a density matrix on the first Hilbert space HA, and then you calculate the von Neumann entropy. So for example, if you consider here the log of base 2, then you can show that if there is no entanglement, in fact, this quantity gives you 0. Whereas if you take EPR pair with base 2, it gives you 1. So this gives you some kind of a way to quantify the amount of entanglement. We can go a little bit further. So suppose, in fact, it is known that in this particular Hilbert space, for example, so if you take any state, and if you take n tensor product of n copies of the same state, and they perform some operation, it's called local operation and classical communication, which is some operation that you can do on this state, which preserves the amount of entanglement, then you can show that you can transform this state into product of EPR pairs. And then the number of EPR pair you have is related to n times this entanglement entropy, and which is actually true asymptotically for large n. So roughly speaking, you can say that this entanglement entropy is amount of EPR pair that you have in the particular state. So it's sort of a way to quantify the amount of entanglement pair. So far I talked about entanglement entropy in quantum system. So let me try to apply this idea to ADS-CFT correspondence. So ADS-CFT correspondence says that gravitational system in ADS is the equivalent to conformal field theory on the boundary. So suppose you have suppose you separate the, so this is a Cauchy surface of the boundary. So conformal field theory is defined on the boundary. So time flows in this direction, and so you take Cauchy surface of this boundary, and suppose you separate the Cauchy surface into some region A and its complement. Then we assume that we think that, roughly speaking, we can decompose this total Hilbert space of conformal field theory into direct product of Hilbert spaces associated to A and A bar. Now, I see Arthur Jaffe in the audience. I see Friedrich in the audience. I see Xu Feng in the audience. And they're flowing. So I should say that actually this is not quite right thing to say. But there is actually a more precise version which conveys this idea, but we just have to say right set of words like Tomita Takesaki, and we should be okay. And in fact, Ed Witten wrote a very nice set of 75-page lecture note on exactly on this subject, posted last week. So if But if I start talking about it, I cannot finish my talk in 1 hour. So let me just say Tomita Takesaki and then done with it. And then for the purpose of this lecture, this is sufficient. So please allow me to continue to use this loose language that Hilbert space become tensor product of Hilbert space defined on A and A bar. That there are better way of saying it. And so if that's the case, then you can apply the same kind of idea that if the Hilbert space is a product of two spaces, then first you take partial trace over the second Hilbert space, define density matrix, and then you can consider von Neumann entropy to define entanglement entropy. So you can do the same thing here, and you take partial trace over this Hilbert space over complement, define density matrix over A, and then you take von Neumann entropy. So there is a beautiful paper by Shinsei Ryu and Tadashi Takayanagi, 2006, 12 years ago, where they conjectured that in the context of ADS-CFT correspondence, this entanglement entropy, if you choose a base to be E, is actually equal to the area of minimum surface subtending A. So this is a boundary region A. And then there is a minimum surface subtending so ending on the boundary of A. Evaluated and divided by quarter with G Newton in it, then it's supposed to give you entanglement entropy. So this was a conjecture formulated by Shinsei Ryu and Tadashi. I should point out Tadashi was actually a postdoc in string theory group here, and Shinsei was a postdoc of Ashwin Vishwana. I'm not sure whether he is here or not, but so there are Harvard connection to both of them. And sorry? Oh, really? Shinsei? Oh, you mean that Tadashi was your postdoc? So you wanted to make a point that he was your postdoc rather than postdoc in string theory group. Excuse me. So this actually led to a very profound development, more detailed understanding of holography, leading to the relation between how this space-time emerged and then coming from the entanglement structure. So here is actually one of the examples of the idea. So if you have a system in finite temperature, there is a standard trick that you can make to describe this thermodynamic system called sum field double state, which is that suppose you are interested in describing this kind of thermal ensemble at finite temperature, then what you can do is that you consider W of the Hilbert space, and then consider this particular state, which gives you entanglement between the two Hilbert spaces. And so this state is called sum field double state. Now, this sum field double state has an interesting feature that if the temperature is small, it's almost decoupled. There are no entanglement between the two Hilbert spaces because only ground state appears. All other high excited states are suppressed because of the temperature. However, if the temperature is large, conversely, all the states are summed up. And so asymptotically, all the states are sort of maximally entangled like that. Okay? So there is a difference between that. And then, so sum field double state nicely sort of intertwine, so to go from this complete decoupled state to maximally entangled state. Now, if you apply this idea to ADS-CFT correspondence and you ask, what is a gravitational dual of this sum field double state? It was suggest, I should have quoted it. So it was actually proposed by Fuanmaru Senna. I'm sorry I didn't put the citation here. That this state is actually sort of dual to maximally extended ADS-Schwarzschild solution, where you have two asymptotic states. So if you consider if you have taken general relativity, you know that if you have a black hole solution, that you can actually extend interior of black hole geometry by analytically continue to the other side, and you have two asymptotic regions. You have same thing for ADS, so you have two asymptotic regions, so you have two CFT in principle, and they are entangled exactly like that. So this strength of entanglement, which I mentioned, so I said that the temperature is actually strength of the entanglement, but in the gravitational side, this actually temperature is related to the size of the Einstein-Rosen bridge. So in some sense, more entanglement you have between the two conformal field theory, the thicker the Einstein-Rosen bridge is. So the entanglement is creating the size of Einstein-Rosen bridge. In the limit of the temperature goes to 0, two sides are totally decoupled. Einstein-Rosen bridge pinches off, but then it's recreated when the temperature is raised. Interestingly, the two papers I just cited, Einstein-Podolsky-Rosen and Einstein-Rosen bridge paper, appears within less than 2 months apart. So I'm not sure Einstein was aware of a connection between them. I'm very curious to know. But more recently, Amartya Sen and Lenny Susskind pointed out that they are actually can possibly be related. So anyway, so the strength of entanglement, namely the number of EPR pair, is proportional to Einstein-Rosen bridge. So that was very interesting observation. The other important observation is that so ADS-CFT correspondence is supposed to give you relation between what happens inside of anti-eta space in the gravitational system and what happens to the conformal field theory without gravity. But you can actually make a final statement by again using Ryu-Takayanagi formula, which is the following. So suppose you have some region A on the boundary, then you have a Ryu-Takayanagi surface subtending to A. So there is actually some kind of region inside of anti-eta space which is bounded by both of them. There is actually a final version of ADS-CFT correspondence conjecture which says that any quantum gravity operator localized in this shaded region between these two can be represented by an operator acting on this subregion only. So there have been lots of works on this subject, and we have actually more detailed understanding of ADS-CFT correspondence. But this leads to some puzzle. This leads to some very interesting puzzle, which I'd like to apply. And I'm telling you about this because I'm going to use this later in my talk, which I guess until 5:50. Good. I was worried that I should end at 5. But OK. So I'm about 2/3 of the way. Actually, I forgot to say, but if you have any question, I'd be happy to take either now or later. So there are actually two puzzles here. One is the following. So this subregion duality says that you can create a local operator here in the gravitational system by using operator only on A. So, but this is puzzling because suppose you can easily consider two regions, like say this is A and this is B, and this is this kind of what you call entanglement wedge. So this same local operator can be described by two different sets of operators. So that means that it seems as though that the local operator in gravitational system is not unique. But there is also this kind of situation where suppose you have you are interested in local operator over here. But suppose you divide the boundary into this 4th segment. So for each one of this segment can only describe operator here. This segment can only describe operator here, etc. None of them covers this region. So that means that operator over here should commute with any local operator on the boundary. And so I guess it's one of the consequences of axiom of quantum field theory that if that happens, this operator should be identity. So this leads to the claim that operators that create local excitation in anti-eta space should be identity and should have multiple realization. And this seems to be totally contradictory. And it should be non-trivial operator because we are creating some states over here. So what's going on? So there was actually a very beautiful resolution to this paradox. So it was actually, this paradox was first pointed out and resolved by Harry, Don, Harrow, and Harrow. Subsequent paper greatly clarified the resolution. So basically the point is that the kind of state we are interested in, the states that can be described by geometry in the bulk and local excitation on it, is actually a very special type of state in conformal field theory, with very special type of entanglement in the boundary conformal field theory, which is very similar to the one used in quantum error correcting code, where these different regions of the boundary conformal field theory share some quantum secret keys. And so by describing this particular type of entangled state, you say that you can find that you can actually, in fact, even in the finite dimensional quantum mechanical system, you can easily construct a situation where you have tensor product of Hilbert spaces. And in this tensor product, you consider particular subspace within this tensor product Hilbert space, which has particular entanglement property between this tensor product, where exactly the same thing can happen. But you can construct an operator on this Hilbert space which has multiple realization, and you can have a situation like that where on each one of this Hilbert space, if you consider operator acting on this Hilbert space, it commutes with that operator. So there is no contradiction there, except that there is actually important realization that conformal field theory states that describe smooth geometry in the bulk and local excitation on that belong to particular class of states, and those are called subspace nowadays. So I would like to actually utilize this type of observation to find some new insight into quantum gravity in this kind of space. So this is actually related to some of the works that I did with Kamran, following up on his initial observation insight 12 years ago. That is related to the first point that I tried to make, which is that Wilsonian approach to low energy theory seems to work differently for gravitational system. So if you have Wilsonian approach, then you can in principle write down any low energy effective action and expect that to be completed in consistent UV theory. This seems to be not the case in gravitational theory. So this leads to the question, given an effective theory of gravity, how can we judge whether it is realized as a low energy approximation to consistent quantum theory with ultraviolet completion, such as string theory? Now, so here I would like to actually focus on the question about symmetry of the theory. So I'd like to remind you that symmetry has played an important role in many aspects of physics, both in identifying and formulating fundamental laws of nature, but also using these laws to understand and predict the dynamics and phases of various matters. So it's used both in high energy physics and condensed matter physics and also astrophysics. You use symmetry to simplify problem, and you use symmetry to find new laws. But in fact, symmetry can also be deceiving. So there are actually two types of symmetry that we should know. One is called gauge symmetry, which is sort of local symmetry. But however, gauge symmetry may not be intrinsic, because two seemingly different microscopic Lagrangian with different gauge symmetry and different matter content can describe the same quantum system, equivalent quantum system. This is called duality. So there are exact duality. For example, N equal 4 super-Yamil theory in 4 dimensions has S-duality symmetry. But two theories that are related to each other by duality can have different gauge group called Lagrange dual gauge group. And so this is the exact relation between quantum theory. There are also sort of equivalence between low energy limit of a theory, and those are called Seiberg duality. So by now we have many examples like that. So gauge symmetry, although it's important in understanding theory, does not seem to be intrinsic in the definition of theory. On the other hand, global symmetry is a well-defined thing. Global symmetry is something that can act on the physical Hilbert space and transform vectors in the physical state vector in the physical Hilbert space. Therefore, it is well-defined and independent of which Lagrangian description you use. However, I would like to argue, and it has been argued also, that consistent quantum theory of gravity does not have such global symmetry. Okay? So gauge symmetry is not intrinsic, and global symmetry does not exist. Now, so here's the standard argument that there are no global symmetry in quantum gravity. So suppose there is a continuous global symmetry, such as SU2. So SU2 has many representation and characterized by spin. And if you have spin j, the dimension is 2j plus 1. J can be arbitrarily large. So if you combine matter with large amount of spin, SU2 internal spin, and make black hole can have arbitrarily large spin. Now, let its Hawking radiate and assume that this global symmetry is exactly preserved. And then so the black hole becomes small, but let's assume that the mass is still larger than Planck mass so that we can still use the Bekenstein-Hawking formula. So then you can get into the situation where the number of black hole state expected by the Bekenstein-Hawking entropy formula is smaller than the dimension of representation of the group G, like SU2. So namely, you can have a situation where 2J plus 1 is smaller, 2J plus 1 is larger than exponential of Bekenstein-Hawking entropy. So namely, that representation cannot fit in black hole once black hole evaporate. So that seems to be contradiction. So that means that the Hawking radiation process, which is supposed to be G-blind, is actually secretly not. Namely, the global symmetry should be violated. Now, this is a good argument, but it's not exact. You can make loophole in this argument. You can find a loophole in this argument. So, for example, how exact that the Hawking radiation preserves symmetry. And you also can ask whether this argument applies to discrete symmetry or finite group, for example. So, for example, in Z2 symmetry, you only have one-dimensional representation, right? You can have either trivial representation or representation where non-trivial element of Z2 is given by -1. So in this case, we cannot apply this argument because 1 is always less than exponential of S Bekenstein-Hawking. So that indicates that this may not be very intrinsic explanation, so you may want to have better explanation. So in my work in progress with Daniel Harrow, which I hope will come out shortly, although I don't want to jinx, based on his earlier work, we have actually proven that in the case of a gravitational theory in untilted space, that the assuming global symmetry is inconsistent with locality of conformal field theory. In view of time, I will not discuss other feature of symmetry that we have also proven in this work. So, but in order to actually prove theorem, we have to define what we mean by global symmetry. So I would like to say a little bit more. I would like to spend a couple of slides on this subject, so please bear with me. So in undergraduate quantum mechanics, we learn that the quantum system has symmetry of group G if for every element of G there is a unitary operator which realizes symmetry and commutes with Hamiltonian. Okay? So this is what we learn as symmetry. But is this really what we want? So for example, you can say that suppose you have a projection operator for 40-second eigenstate, then they exponentiate it. It's commute with Hamiltonian, and so it's nice symmetry, but we don't want to call that as a symmetry. It doesn't have nice locality in the context of quantum field theory. So we need to actually, we'd like to make additional assumption which captures some locality of quantum field theory. So here is a set of requirements that I would like to impose. One is that symmetry should map local operator into local operator. And such transformation should be faithful. Because if it is not faithful, you can always divide that by some sub-element of the group that acts trivially on all local operator and done with it. And then, and also we require it should commute with energy momentum tensor. Yes?
Is this supposed to be a requirement in quantum field theory or quantum gravity?
Well, we apply it for both. And so then you can ask what we mean by local. So in the case of gravitational system, what we mean by local is that local within the within the Planck length scale, and so we require that we have quasi-local operator, which can be represented in the boundary CFT in the way that I sort of discussed over here. So in the gravitational system, we say that gravitational system, so I would like to prove that gravitational system does not have global symmetry. And so what I would like to do is exclude the possibility that you can have a local excitation in gravitational system like this, having this kind of property that transform non-trivially under this global symmetry. That's what I mean. So I would like to define global symmetry in this way and exclude that possibility in this context. Okay, so those are the three requirements, and I believe that those are fine with you mostly. But I would like to actually impose one more requirement, which is a little bit more technical, but I should say it because it plays an important role in this construction there. So which is to say, first let me state it and let me explain. So suppose, this is a Cauchy surface of the boundary quantum theory. So suppose you divide it into product of some union of some subspaces. then we say that there is actually a symmetry operator acting on each of these subspaces, and this symmetry generator is a product of this. Okay? So this is an assumption. Now, is this a reasonable assumption? So let me try to motivate that. So suppose G is a continuous symmetry. Is there chalk? You don't use chalk at Harvard? Oh, great. So suppose G is continuous. Then you have a Noether theorem. So that means that you have a current. So the symmetry generator is an exponential of integral of Noether current, like this. So if sigma is, say, R1 union R2, this integration region becomes sum. So that means that you have U of R1 times U of R2. So this is such a simple statement. So if this is if you have a Noether current, then obviously you have this kind of property. So, but I would like to. So this is sort of a replacement of Noether theorem because I want to use it for discrete symmetry as well. So discrete symmetry, you don't have Noether current, but this actually property can still hold. And in fact, for large class of quantum field theory, this is a true statement. And in order to actually precisely state what this is, again, I have to say words like Tomita Takesaki, but let me not do that because I would embarrass myself in front of Arthur. So, but in fact, for continuous symmetry, one can actually show that if you believe 1, 2, 3 by Noether theorem, this is true. And for more generally, if you assume what's called split property assumption, then it has been shown that this is also true. So the basic idea is that if the Hilbert space yes? Did anybody ask a question, or is it okay? So in view of time, I'm going to skip this, but you can actually give some explanation of why the split property leads to the tensor product property of symmetry operator. So now I'd like to apply the kind of thing that I talked about, this subregion duality, to show that if you assume symmetry to have this kind of property, then you cannot have global symmetry in ADS gravity. So here's an idea. Here's an argument. Suppose gravitational theory in isolated space has global symmetry G, which I would like to say, I'd like to show that that's not possible. But in contrary, suppose you assume this, then there must be a bulk local operator that transforms faithfully into another local operator at the same point, in the sense that I described in the earlier. So we say that symmetry generator is a tensor product of this type. Now suppose you have local operator residing over here. Now you take the boundary to be sufficiently small segment, then each of these entanglement wedge does not reach this point. So that means that this operator should commute with this operator because they are at different region. But this is contrary to the assumption that this local operator should transform faithfully. So this is a contradiction. So this shows that it is not possible. So by preparing precisely what we mean by symmetry, we can show in one page that the gravitational system in isolated space cannot have global symmetry. So now I have like 5 more minutes. So I'd like to say a few things about weak gravity conjecture, which is actually sort of generalization of the statement that there are no global symmetry in quantum theory gravity. So this is a statement that in any low energy theory described by Einstein gravity plus Maxwell field plus finite number of matters, if it has a Ewing completion as a consistent quantum theory, there must be a particle of charge Q with respect to this Maxwell field and mass m much less than Planck scale, such that this inequality is satisfied. It's called weak gravity conjecture because if this inequality is satisfied, then the gravitational force between them, gravitational attraction between these particles, is weaker than the Coulomb repulsion between that particle. So this was conjectured by Nima, Al-Khani-Hamed, Lubos-Motor, Qumran also at Harvard at the time, the Nima and Lubos. So this was motivated by black hole physics. This is less well motivated by the no global symmetry argument. But there are some good arguments for this conjecture. And for me, more importantly, it is known to be true for any known construction from string theory. And then there are holographic motivations, which I do not have time to discuss. But interestingly, in all cases, unless equality is protected by supersymmetry, it's actually a strict inequality. So in fact, when they wrote this paper, people always asked, is inequality required or not? So since this was asked, so Kumar and I conjectured a couple of years ago that, in fact, you should be able to drop this inequality. So we call this a sharpened weak gravity conjecture, unless equality is protected by supersymmetry. So, but by conjecturing that, we led to a stronger conjecture that if you have a gravitational theory in ADS, if you don't have supersymmetry, then it must be unstable. And in fact, interestingly, all known construction which does not have supersymmetry is marginally stable at best, and some of them are unstable in an interesting way. To be fair, constructing examples without supersymmetry is hard, and so this might not be a strong argument, but the way that they fail is very interesting, so let me mention some of them. So as soon as ADS-CFT correspondence was proposed, maybe this is like 4 months after this was proposed, Eva Silverstein and Shamit Kachru pointed out that if you divide this ADS5 cross S5 in type 2b, which is a canonical example of ADS-CFT correspondence, by some discrete group acting on S5, then you can break supersymmetry if this discrete group gamma does not fit in SU3. So this, of course, S5 has SO6 symmetry, and then SU3 is a subgroup of that. And if gamma does not fit into that, then supersymmetry is broken. But later it was found that, in fact, this construction is unstable. So if gamma has a fixed point in S5, it turns out that there is a string state which is a twisted sector under gamma, which actually is a tachyon, which breaks the Brighton-Friedman bound, so which creates instability. And if it has no fixed point, then it turns out that there is actually a so-called Witten's-Carter-Klein instanton, which is created in the middle of ADS and eats up the whole space. So in this case, this construction seems to fail in a very interesting way. Now, after we published this paper, I got several inequality from distinguished member of our community saying that I have this construction, how about this? So we are able to refute most of them, but there was actually one interesting one which was pointed out by Hervé Riard and his collaborator, which is ADS5 cross CP3 in M-theory. So I got worried about this because they constructed an example which breaks supersymmetry and which does not have obvious instability mode. So there was this first-year graduate student at that time, he's second year now, who just came in and said he needs some program. So I gave him this program, and within a month or two, he came up with actually Witten's generalization of Witten's instanton, which is, in the Witten's instanton was an example where you have a non-trivial pi1 in the geometry, which shrinks in the middle and eats up the space. Now, so this CP3 doesn't have pi1, but CP3 has pi2. So I told him that let's try pi2. So he actually came up with an exact solution where pi2 shrinks in the middle and eats up the space. So you see that this conjecture leads to various interesting type of instability. And this actually also leads to various interesting new observations about even our standard model of particle physics. So Nimar Kani-Hamed again and his collaborator pointed out that if you start with our standard model of particle physics, the one that is actually we observe in the laboratory, coupled to Einstein gravity, and just consider that, and then compactify this theory down to 2-dimension or 3-dimension by compactifying on torus or circle, then what happens is that we know in 4 dimensions that we have cosmological constant. But cosmological constant is very tiny. Now suppose that, assume that as an input, and then compactify on a circle, then there are lots of particles going around that create Casimir energy. Casimir energy contributes to the cosmological constant in 3 dimensions. So depending on the particle content of this 4-dimensional theory, it gives rise to either positive or negative cosmological constant in 4 dimensions. The lightest particle in standard model is photon. The next lightest particle is neutrino. So it turns out that what kind of geometry you get in 3 dimensions depends on the type and masses of neutrino. And in certain cases, it gives rise to Untitled space in 3 dimensions. And then this is apparently stable. As far as within the framework of standard model capital Einstein gravity, it seems to be stable. That was pointed out by Nimar Kani-Hamed. So Kumar and I thought, well, if you assume that there are no non-supersymmetric ADS, which is stable, then this has to be stable, but it's contradiction. So that means that this type of neutrino mass is prohibited. So we conjecture that if this line of logic is correct, then neutrino cannot be Majorana, because if Majorana, actually neutrino would predict that. Now, this idea has been explored further recently and leading to various interesting constraints on standard model of particle physics. And in fact, also possibility of how to extend the standard model of particle physics, because whether this construction has instability or not also depends on some particle states. So this was actually pointed out in the paper that just appeared last week by a Madrid group, where depending on how you extend standard model, that feature of the instability changes. So this might also give you some constraint on what kind of particle physics model we have beyond standard model. So these are all interesting. So this suggests that, in fact, the connection between ultraviolet and infrared degrees of freedom in gravitational theory are rather different in the gravitational system and may lead to some surprising infrared prediction on observable phenomena from ultraviolet completion of quantum gravity. And many of these developments are inspired by knowledge of quantum information theory, so it can provide some key to open the secret in quantum gravity. So that's more or less what I wanted to say. But I have one more thing that I would like to make, which is that I'm organizing string theory conference in 3 months in Okinawa in Japan. And so actually, I am also organizing a related conference a week before in Sendai. So we have these 2 conferences. And the point of my presenting this is to attract your attention to the fact that we have funding for student and postdoctoral fellow to come to this conference. If you submit your poster and title and abstract, by the end of this month, we have 18 slots of this fellowship, which covers your economy class airfare to Osaka, to Okinawa. So please remember to apply to that. Okay, with that, thank you for your attention.